Good evening. My name is Bozan George Andrei, and I'm going to present you uh, quantum communications with optical vertices. This is the title of an article that we sent to PRA, I mean Physical Review A, and we hope that it's gonna be published there. What is this all about? Why do we need quantum networks? The idea is that quantum computers have developed so much that actually they can represent a threat to the internet security and the public key cryptography by being able to break them. And that's why we need to construct uh, better when it comes to better quantum networks when it comes to security. Uh, One way we can achieve this is by actually creating uh, entanglement with spin or uh, polarization entangled protocols, or maybe protocols that actually can have a stronger key that cannot be broken that easily. And that's what we will be talking about here in this poster. Uh, it is worth to mention that actually uh, most of optical device communication networks use photons to encode information. Uh, and for this reason, uh, people created uh, space division multiplexing and wavelength division multiplexing. But we are going to discuss today about communication using optical angular momentum, more exactly optical vertices. What are optical vertices? Optical vertices are the interference patterns in which photons uh, have orbital angular momentum, and their trajectory, their wavefront looks like this. It's like a helicoidal trajectory. Uh, the OIM of the photon can be changed by using spiral phase plates, as you can see here. Uh, our optical our optical quantum networks will be based on quantum sorters mainly that look like this. So here we have the Fourier gate, d-dimensional Fourier gate, and its inverse. And here we have a couple of z gates, and we have to observe that actually these uh, sorters have their own inverse, which looks like this, like this. Here we have the Fourier gate, its inverse or complex conjugate, and here we have the same z gates, but actually their order is reversed. This is how their actions look like, where minus and plus circled represent subtraction and addition mode D. We have also to note that the sorters have the period D, which is an important property, and we are going to use it in the following protocols. So we start with the first type of protocol, which is the point-to-point architecture. Here we have D pairs of sender and receiver connected through a single channel SD, where SD is the multiplexer and the SD cross is the demultiplexer. I mean the other way around. SD is the demultiplexer and S cross is the multiplexer. And here we have the action of this protocol. And here I show you an example for D equals 2. And we have two senders and two receivers. So here Alice uses 0 OIM to communicate with Charlie, and Bob uses 1 OIM to communicate with Diana. Here we have a point-to-point architecture, point-to-multipoint architecture. This is the second type of protocol that we're going to discuss about. We have DS senders and DR receivers. We are going to discuss here about two types of point-to-multipoint protocols. In the first one, we have the number of senders and the number of receivers to be coprime numbers. And thus, the sender S, if he wants to communicate with the receiver R, then he has to prepare a state OIM which respects these equations. And here we have a diagrammatic example where the number of senders is 2 and the number of receivers is 3. Here Alice, to communicate with Charlie, she needs to prepare the state 0. If she wants to communicate with Diana, she has to prepare the state 4. And if she wants to communicate with Eve, she has to prepare the state 2. Bob, if she wants to communicate with Charlie, she has to prepare the state 3. If he wants to communicate with Diana, he wants to create the state 1. And if he wants to communicate with Eve, he wants to create the state 5 in all terms of OIM. Now let's go on the second type, which is the general case. Here we don't need the condition anymore, the coprime condition. But when it comes to the multiplexer, we'll have dr and dr times d as dimension. So we'll have this dimension, dr and this dimension. Here we had ds here as the multiplexer dimension, and dr here as dimension for this sorter. And here we have a table in which we noted every single OIM state in order any sender to send to any receiver information. And we'll have here a diagrammatic example again of a point-to-multipoint protocol in general terms, general case, for ds equals 2 and dr equals 4. Here Alice, if he wants to communicate with Charlie, he has to prepare the state 0. If she wants to communicate with Diana, she has to prepare the state 2. If she wants to communicate with Eve, she has to prepare the state 4. And if she wants to communicate with Felicia, she has to prepare the state 6. If Bob wants to communicate with Charlie, he wants to prepare the state 1. If he wants to communicate with Diana, he has to prepare the state 3. If he wants to communicate with Eve, he has to prepare the state 5. And if he wants to communicate with Felicia, he has to prepare the state 7. Now let's get on to the fully connected network. Here we have an n-dimensional quantum sorter for n users, and all the users can communicate with each other. And here I can show you an example when we have 4 users and a 4-dimensional protocol. Actually, this is a very interesting protocol that can be used in many, let's say, communication tasks. Like for instance, when you have the Taiwan government communicate with Romanian government, or with or communication between different buildings or different banks, for instance, there could be an interesting application here. Now let's pass on to the theme of this conference, and let's talk about the entanglement distribution protocols. And here we have two types of protocols in which uh, the initial state is polarization entangled. The first type of protocol is almost the same as the previous one, because here we use the fully connected network. We have Alice and Bob entangled. I mean, sorry, not really fully connected, maybe a protocol like this. Alice that desires, let's say, to communicate with Charlie has to prepare 0, communicate with Diana has to prepare 2, to communicate with Eve has to prepare 4, communicate with Felicia and has to prepare 6 OIM, and so on. Bob is the same logic. This can be seen here. Now the second one is a little bit more interesting. It's a passive OIM network, and it has this figure. It has this protocol, this scheme, and this is an interesting one. Here we start with the state 0, 0 in terms of line, 0, 0 in terms of path, and each photon, the signal and the idler, passes through a Fourier gate. And thus we have the following state, like this. And here is this OIM. I'm sorry for not writing this out. And after passing through the Fourier gate, each photon will have to pass through one of these 10 CBPs. Thus, the quantum state will become like this. After passing through one of this, after each photon passed through one of these CBPs, she will have to pass through a gate. Sorry, through a sorter, each one through a sorter, and you will have the final state will be like this after this movement, and then both photons will be multiplexed into one single channel, and by that I mean one single sorter. Each photon will pass through one single sorter, and the final state will look like this, where here the +1 for the second state comes from the fact that the idler will get through the how do I say it, through the path 1, and here the signal passes through the path 0. So in conclusions, I presented you a few protocols, the last two of them being entanglement based, and these protocols can be used for a wide range of communication tasks, such as communication between satellites, or communication between banks, or communication between governments, and so on. This was all that I had to present to you. Thank you for listening, and I'm awaiting your questions.